Okay, so we are down to our last talk. It's my great pleasure to introduce Dr. Evan Schneider. She and I went to grad school together at, of course, the greatest university, the University of Arizona. That was a joke for all the faculty here. And since then, she's been a Hubble Fellow at Princeton, and today she's going to tell us about outflows and galaxy evolution and the circumgalactic medium. So, Evan.
Yes, thank you. So first of all, thank you so much to the organizers. This has been, so what's this one for?
That one's for the video.
Oh, okay, here, all right. So many. All right. Okay, is it good? Yeah, okay. Thank you to the organizers. This has been a really, what button?
There's one button.
Oh.
Right here. There we go. Now it's on. Okay.
All right. Third time's the charm. Thank you to the organizers for this wonderful and unique symposium. It really is different than anything I've ever been to, and I think it's really neat that it has carried on for all of these years. So today I'm gonna present some work. Originally, I think I titled my talk "Outflows and the CGM." What do we know? But given the breadth of expertise that has been displayed throughout this conference, I thought I could expand my title a little bit and take on all of galaxy evolution. So I'm just gonna frame the big picture before I get into more specific details. So to start from the perspective of galaxy evolution, I just wanted to make the point that there are a number of observations that point to the importance of stellar feedback in the evolution of galaxies. And so we have a few lines of evidence. One of the most obvious is the stellar mass function of galaxies. So this plot shows on the x-axis, this is just the log mass of galaxies, so different mass bins, and on the y-axis is their number density in space. And the yellow points here show you the data for the redshift 0 galaxy stellar mass function. The blue dashed line shows you what that function would look like if you just had a dark matter halo mass function, and each halo had its sort of cosmic fraction of baryons of order 15% of the mass. And what you can see is that particularly at the low masses down here and the high masses, there's a dearth of baryons in the stellar content of galaxies, which implies that something must have pushed those baryons out of those systems. Otherwise, they should have formed stars. Similarly, there's, like I said, many lines of evidence. Another is just the general star formation rate and gas content of galaxies that we observe. So there's a lot going on in this plot, and it's not something that you need to digest in full, but essentially this is the gas surface density of galaxies over a large magnitude range in surface density divided by the free fall time of the gas. And plotted on the y-axis is the star formation rate surface density, so how many stars are forming. You can see that there is this relatively compact linear relationship. And one of the things that's interesting about this relationship is that if you just assume that some fraction of the gas is forming into stars every free fall time, you end up with an efficiency of about 0.01 or 1%. So only 1% of gas is forming into stars per free fall time. Why is that? We think it has something to do probably with stellar feedback. Another line of evidence is the metal content of galaxies. So metals are formed in stars. But we find, again, now showing the log mass of galaxies on the x-axis and the mass of metals in galaxies on the y-axis. If you add up how many metals galaxies should have formed over their lifetimes, and then you add up a sort of census of the metals that we find in galaxies, so this is metals in stars, metals in the ISM, and dust, you find that you fall short. So galaxies seem to be missing many of their metals. And the most appealed to answer for why these metals are missing from the galaxies themselves is that they have been ejected via feedback mechanisms. Another way of thinking about this, oops, there went a little fast, is we can also observe directly that there are metals outside of galaxies. Right, so here, this is just a study from redshift 2 galaxies that have been stacked. This impact parameter is just showing you as a function of distance from the galaxy the equivalent width in various metal ions. And this, again, is from a population of galaxies, but what you can see, all I'm trying to demonstrate here, is that, out to relatively large distances from galaxies, already at redshift 2, there's significant amounts of metals in the gas. So again, implying that something has been responsible for removing these metals from the galaxies themselves. So there's some observations that indicate that feedback is important. An important tool in the last couple of decades for modeling galaxy evolution has been cosmological simulations. So most of you are probably familiar with the general idea. We take a box that represents a volume of the universe. We input the physics that we think is important for galaxy formation. I've listed that physics here in sort of my impression of how well we think we understand it. So gravity, we think we understand pretty well in the context of lambda CDM. Magnetohydrodynamics, we have very robust solvers in our astrophysics codes that have been well tested. Gas cooling and heating is relatively fundamental physics. There are caveats that have to do with ionization, that sort of thing. Star formation, okay, there's a field that is dedicated to understanding that problem better, but on the scale of cosmological simulations, we've developed relatively robust so-called subgrid prescriptions. And this last one, feedback, I would argue, is where we really, it's very uncertain what we should be doing, which is what much of the rest of this talk will be about. So you include all of that physics, pick your favorite example of a cosmological simulation. Here I'm showing the Illustris on the left and Illustris TNG simulations on the right, just because they've done a very nice job of comparing two simulations with exactly the same initial conditions where the only thing they changed was the feedback. And what you'll see is that the way that that feedback is implemented has large changes on the galactic structure and the larger scale structure of the universe. And so here, this is actually the gas temperature that's being shown. And at early times, it's relatively similar, but as this simulation progresses, you'll see that one of these boxes ends up having, for example, a lot more hot gas in the space in between galaxies. There are more subtle changes as well in terms of things like the metal content of the gas outside of the galaxies and in the intergalactic medium. Okay, so what we would like to do is take these simulations that represent our best guess of how galaxies are evolving in a sort of cosmological context and compare them to observations and then learn something about how galaxies evolve. And so anytime that someone runs a cosmological simulation, writes a paper about it, you'll often see plots like this. So this is, again, the stellar mass function of galaxies and their number density in space. And the white points are the same points that I was showing you earlier. And here's a bunch of different simulations and how well their simulation fits this stellar mass function. As you might imagine, this one came from the Mufasa paper because it goes through the line the closest. But the point I want to make here is that actually just comparing these data and these simulations doesn't really tell you very much, at least about, for example, feedback, right? Because the problem is that these observations were used in order to calibrate the way that you implemented feedback in the simulation, and therefore you can't actually learn anything about the feedback itself from doing this type of comparison. So what you have to do is you have to find observations that were not involved in creating the simulation and use those to try to discriminate between your different models. There are sets of observations like this. One of them, for example, that has been used widely in the last 5 or 6 years is the gas that's outside of galaxies. So the gas in the galaxy halo, the circumgalactic medium. This is from a 2017 review paper about the circumgalactic medium. And here again, this is the log mass of the galaxies. And this is the cumulative fraction of mass in various different phases and stars, et cetera. So in this case, the stars, this is the mass of the stellar mass function. Then you have mass in the ISM, and these bars are representing 2 different surveys. This was from the COS Halos survey that looked at, for example, L-star galaxies at low redshift. This COS dwarfs looked at dwarf galaxies at low redshift. Hatched is sort of their upper limit for how much gas they think is in these different phases. Solid is the lower limit. What you can see is there's a lot of gas outside of the galaxies, depending on which of these limits you believe. For example, in L-star galaxies, maybe we've solved this missing baryons problem. We found all of them there in the halo. But interestingly, if you make this comparison with cosmological simulations, here on the left is the same sort of plot, but for a set of simulations run with the Gadget code. On the right is the plot for the Illustris simulation that I was showing on one of those previous slides. You can see that they actually do look very different in terms of how much gas do they predict is in the halos of these galaxies, and what phase do they think that it is in. Is it hot? Is it cool? Is it intermediate? So that's good. We have a set of observations that we could use to try to discriminate between these different models. But it's still a challenging problem because these feedback implementations in these large-scale simulations are almost arbitrarily complicated. And so what I mean by that is that you have to make a bunch of different choices when you're deciding how to do feedback. And those could include things like, do you do active versus preventative feedback? What do I mean by that? Active feedback, where you have stars form in some gas and then you throw gas out of your galaxy as a direct result, versus something like AGN feedback, where you're not necessarily coupling to the gas, you're just heating gas in the halo and preventing it from accreting, right? Those are decisions that you make when you're coming up with your model. Winds versus fountains. Do you eject gas fast enough to leave the halo, or do you just eject it such that it should sort of hang out in the halo for a while before it reaccretes and can form stars? Do you use stellar feedback versus AGN? Not all simulations agree about what amount of energy they inject in either of these sources, or whether they include AGN at all. And there are some uncertainties that are pretty difficult to get around. So for example, all of these sources of feedback are completely unresolved in the simulations, right? You're not resolving individual supernova events, and you're certainly not resolving, the accretion disks of AGN in these simulations. So you have to have some sort of subgrid prescription for how you do this. Some phases of gas remain unresolved in these simulations. So even in zoom-in simulations of galaxies, you're not resolving the hot phase of supernova feedback, right? And that's the phase that we think drives these winds, so that might be important. There's also the question of whether or not we're still missing physics. I listed a bunch of physics that's sort of generally included in these simulations, but lately it's come to light that maybe we need to care about cosmic rays, and maybe there's these other sources of physics that we haven't considered that are also contributing to our uncertainty about whether the models that we have are correct. So I would argue, based on some of these challenges at least, that one major challenge that's currently facing cosmological simulations is that we just don't have enough numerical resolution to, come up with a predictive model of galaxy formation as it currently stands. Okay, so I've outlined a few major outstanding questions that I think are related to this background that I've been presenting. And I think all of these questions are interesting. I'm working on all of them in various different ways. One is, how does the star formation feedback directly affect the interstellar medium and regulate future star formation, whether that's by blowing gas out of the galaxy or simply, injecting turbulence into the interstellar medium? How are outflows generated from the gas, and what physics is determining their individual properties? And then what happens to outflows as they propagate through the circumgalactic medium, and what is the structure of the circumgalactic medium? So the observations that we have don't actually do a very good job constraining, for example, if you have gas in multiple phases, is it contained in sort of clouds in a background hot medium? Are there large structures? Are there small structures? How does that change with redshift and the mass of the halo? And those sorts of questions. So that's a lot. In this talk, I'm mostly going to focus on this central bullet point, how are outflows generated, because that's where I've been focusing a lot of my time and effort in the last couple of years. So one approach to this problem is to combine small-scale simulations with these sort of guiding observations, perhaps more detailed than the macro statistics I've been presenting, in order to answer some of these questions. And that's the approach that I'm going to be taking and that I took in the work that I'm presenting today. So I'm going to dig into a specific example that's related to outflows, and I'm going to present some of the observations that were my guiding observations as I was coming up with my model and the small scale simulation that I wanted to run in order to answer this question. So this is the iconic starburst galaxy M82. It's a nearby starburst, so it recently underwent a burst of star formation in the central nuclear region. That created a lot of hot 10 million Kelvin plasma. You can actually see that in the hard X-rays from this composite image. That's Chandra data. And you can see that it's also blowing out this wind. So this is why this is an iconic image. You have this edge-on galaxy, and we can see all of this really well. It's spatially resolved because it's so nearby. You can see in the soft X-rays, that's the blue data. There's this million-degree gas that seems to be sort of filling this perhaps biconical structure. And interspersed with that is both H-alpha, which is this sort of yellowish phase that's tracing the H-alpha filaments, and even cooler gas that's traced by the dust. So the red in this composite is Spitzer data. And one of the things that's unique about this image is that we can actually see all of these different phases. So people love studying M82 because it's one of the only systems where we can really in detail see all of the different phases of gas and get detailed information, for example, about its kinematics. Related to the observations I was presenting earlier in the halos of galaxies, there have been a number of surveys done in the last 5 to 6 years using the cosmic origins spectrograph that was installed on Hubble in order to probe the circumgalactic medium of low redshift Z=0 galaxies. This is an example of data from a combination of many of those surveys. Again, here on the x-axis is the impact parameter. So each of these points represents a single sight line. If you're not familiar with these sorts of quasar absorption line studies, this is my schematic of how this observation works. You have a background quasar. It is intercepted by some cloud of gas that's outside of the galaxy, and that creates an absorption line. Here I'm showing the equivalent width of neutral hydrogen for a bunch of these different systems. Red and blue represent star-forming and passive galaxies. So one interesting thing that came out of these studies actually is that there's a lot of cool gas, where cool in this context means 10 to the 4 Kelvin, in the halos of both star-forming and passive galaxies, which our naive expectation of how galaxy halos forms indicates that halos should be hot. The gas as it accretes should go through a virial shock, and that should create this hot, relatively hydrostatic atmosphere. And so it was actually a bit of a surprise. These sorts of observations have also been made in many low ionization state metal lines. Bit of a surprise to find all of this cool gas out in the halos of L-star galaxies. Another interesting observation is these blue shifted absorption lines that we often see when we look at star-forming galaxies, particularly star-forming galaxies that are forming stars above some certain threshold of order 5 or 10 solar masses a year. And this is how these sorts of observations work. This is what we call a down-the-barrel observation. So now the continuum source is actually the stars in the galaxy itself. Again, that light is intercepted by some intervening gas. In this case, I'm assuming the gas is outflowing, and that means it will be blue shifted on its way to us. That's what this observation shows. So this is a stack of galaxies around redshift 1. These nebular lines from the gas in the interstellar medium show you the rest velocity of the galaxy. And if we look, for example, at this magnesium-2 doublet, you can see that you have gas, at blue shifts all the way up to, say, 600, 800 kilometers a second. Again, because this is a low ionization state line, we interpret this as relatively cool, say 10 to the 4 Kelvin gas that's moving quite quickly. I don't have a time to get into right now why that in and of itself is something of a puzzle, but it's something that I'll come back to later. So remember, one of the things that's interesting about this is not just that the gas is outflowing, but that cool gas is outflowing relatively quickly. So the motivation behind the set of simulations that I'm going to present was essentially, can we create a theory that explains all of these various observations in detail? So we want a sort of physically motivated model, say something that has to do with stellar feedback, that can reproduce the multi-phase nature of these outflows, also the velocity structure in the different phases, and we like it to be able to transport metals out of galaxies to the CGM and the IGM where we see them. And one of the reasons that this was an interesting and challenging problem to work on is because it covers a large dynamic range in scales. So for example, if we think stellar feedback is responsible for these winds, then we care about this region in the disk where supernovae are actually exploding. Depending on how clustered they are, maybe we care about individual supernova remnants of order 1 to 10 parsecs in radius. But then, on disk scales, you can have sort of global starburst events, so we probably care about the global geometry, which gets us out to 1/10 kiloparsecs, say. And if we want to trace these outflows out into the halo, you're now looking at something like 100 kiloparsecs for the virial radius, and this becomes a very challenging problem. The reason it's challenging is because you really need high resolution in this entire volume, because the physics at play, these hydrodynamic interactions, say, between hot and cool phases, require very high physical resolution in order to capture the mixing and shocking and cooling properties that are going on in these outflows. And so this is a problem that would be difficult to study, for example, with a Lagrangian or adaptive mesh type code. Fortunately, I have a code that I can use to study this problem. So a little bit of reverse engineering there, perhaps. But part of my PhD thesis was building an astrophysics hydrodynamics code that could tackle these sorts of problems that require high resolution. So this is the code. It's called CHOIA, which stands for Computational Hydrodynamics on Parallel Architectures. And the reason it's called that is because it was designed to run on graphics processing units. So that's a highly parallel architecture. I was a little disappointed yesterday when you were all asked if you're familiar with GPUs, and very few people raised their hands, because in fact you all use GPUs every day, I guarantee it. They are the video cards that are in all of your computers. So you're at least as familiar with GPUs as you are with CPUs. Nevertheless, we built this code, and the idea is just that we can run really fast hydrodynamics problems because we're taking advantage of this new architecture. It's a publicly available code, and so if you're interested in more details, you can check out the papers or the code itself. One of the advantages of having built this code that runs on graphics processing units is that these GPUs are being installed in the largest computers. So for example, Titan was a DOE-funded supercomputer that had 18,000 nodes, each of which had an NVIDIA GPU. This was, at the time that it was built, the fastest open science supercomputer in the United States. This slide is actually very out of date. Titan was installed in 2012, and so that's not actually true anymore. Now there's a bigger computer in the same lab, but nevertheless, a huge amount of power in this system, and we were able to take advantage of this because we had this specialized software. So to run the simulations that I'm going to talk about, we got an allocation of computing time on Titan through the InSight program, and I designed this experiment. And so this was my idea. I was going to design this set of simulations that we could use to study outflows in a region of parameter space that's interesting because it was one that we hadn't really probed before. So I decided we're going to model it sort of after the M82 system because that's a system that we have a lot of data on. And the idea was then to have a box that's 10 kiloparsecs by 10 kiloparsecs by 20 kiloparsecs in size. In that box, I'll place a disk of gas. I'll inject some mass and energy into that disk to represent the effects of stellar feedback and supernovae. That will drive an outflow, and then we'll study this system. All of this is going to be done at constant resolution. So we have 2048 by 2048 by 4096 cells in each of these simulations. That gives us a resolution of just under 5 parsecs in a given cell. And so what's unique about this, right, is that, like I said, this is a region of parameter space that hadn't been explored for this kind of problem. So if I plot, for example, volume elements, by that I mean, my case cells. If you are familiar with smooth particle hydrodynamics codes, that would be the particles, the hydrodynamics particles, against the average resolution in the simulation. And of course, this isn't fair for, say, a cosmological simulation because they have much higher resolution than this in galaxies themselves. Nevertheless, because they cover a very large volume, they have relatively poor resolution outside of galaxies, which is why it's challenging to study, say, outflows in the circumgalactic medium in a cosmological simulation. What you can see, these are sort of, like I said, cosmological simulations sit in this region of parameter space. Zoom simulations sit in this region of parameter space. These are simulations where people actually just simulated pieces of disks, so patches of the ISM, for example. And we're sitting over here where we've basically taken a cosmological simulation worth of resolution and just applied it to a single galaxy. Right? So this really is different than what other people have done. And so this is a sort of basic setup for one of these simulations. We have this box, as I said. I just initialize it with an isothermal disk of gas at 10 to the 4 Kelvin. So it's initially in this stable equilibrium. The gas is rotating. And we have a gravitational potential that's static. So I'm not going to run these simulations long enough that we think that the dark matter potential of the gas or the stellar potential should change significantly. And I run all these simulations at multiple resolutions so we can check for features like convergence in the properties that we're measuring. I'm going to take a tangent here because something that is important is to understand then how much mass and energy should I inject into that disk to represent the stellar feedback? And there are many different ways that one could think of doing this. I'm not in these simulations going to actually simulate and evolve a multi-phase ISM and self-consistently form stars. Okay, that wasn't the purpose of this particular numerical experiment. So I need some way of coming up with a reasonable model for how supernovae are going to inject mass and energy into the disk in order to study the properties of the outflow, which is what we're really focused on. And so to explain how I came up with this model, I'm going to briefly take a tangent into some relevant facts about the ways that stars form. So this is a bit of a broad talk. First of all, stars form in clusters. So, this is an image of the spiral galaxy M33, which is forming lots of stars, and you can see in this spiral arm these, beautiful young stellar clusters. And it's also the case that bigger stars tend to form in bigger clusters. And so if you care about stellar feedback and the effects of stellar feedback on galaxies, then really what you care about are these clusters. And in particular, you tend to care about the most massive clusters because they are responsible for injecting the most energy. Another relevant fact is that if you have supernovae that are exploding in a star cluster, they're exploding in an environment that has already been affected by previous explosions. And this may seem obvious, but for many years in the sort of supernova interaction with the ISM community, we were mostly focused on sort of single supernovae and how much momentum that one supernova injects into the ISM, because in the case of the Milky Way, that's probably the dominant source of momentum injection. But in the case of large clusters that are going to drive outflows in things like M82, we really care about this clustered environment. And so you can see, this is an example of a superbubble in the Large Magellanic Cloud where you've evacuated already this interior, and so subsequent supernovae are going to explode in a region that has already been affected by those previous explosions. So what we did in order to come up with a model for our mass and energy injection in our large-scale Seagull simulations was ran this series of smaller simulations. So I call these superbubble simulations. And the idea there is I take a box. This is a projection in temperature through a box. And I allow thermal instability to set up a genuine multi-phase medium. So here, if you look at the temperature scale, we're getting down into, say, the cold neutral medium and the warm ionized medium. Once we have a stable multi-phase medium, I make an assumption about the mass of the cluster that is going to form here, and then I say, based on the number of supernovae that should go off over some period of time, say 30 million years, I can create a rate of supernova explosions. And then I just inject supernovae at that rate, and I can measure all sorts of properties of this system. And this is actually an entirely separate project that I'm not going to talk about very much, other than to say that this is how we're going to come up with our mass and energy injection rates. And what I mean by that is that if I now show you a density slice through one of these simulations, and I've placed a sphere onto this, and then I'm going to do the same thing, start setting off supernovae in the center. And then this plot on the right shows you, as a function of time, the mass the mass injection rate through this sphere, the mass flux, right? This mass flux is essentially the subgrid model that I need for my large-scale simulations, right? So the idea is that I'm going to assume that I know the properties of the average properties of the ISM in my big simulation because I set the gas surface density. And what I want to know is, given some number of star clusters, how much mass and energy should be injected at each point in that simulation. And that's exactly what I'm measuring in these smaller simulations. So I have m dot, and I also can measure e dot. Okay, so that's what I did. So this is now, finally an example of one of these large box Seagull simulations. And in this one, I am using these subgrid models for the clusters. And so on the left is a density projection through the box. On the right is a temperature projection. So purple represents 10 to the 4 Kelvin gas. This kind of pink color represents about 10 to the 6. And you'll see when it gets started, there's hotter gas that's represented by sort of yellow colors. And I'm going to start this. I'm going to arbitrarily put clusters throughout the center of this disk. Center because we're comparing both to M82, and we wanted to come up with a sort of spherical analytic model. And I have those clusters rotating with the disk, and I'm injecting mass and energy in the clusters according to this subgrid model that I described. And what you'll see is that it creates this, outflowing multi-phase wind. So this is great because, we actually have cool clouds of gas that are embedded in a background hot, fast medium. You can see it sometimes there's actually significantly more cool gas relative to other times. I can arbitrarily change the, quote, star formation rate in this simulation by just turning on fewer clusters. So that's what I did at later times. That's why you're seeing the sort of overall properties change. But actually, no matter what star formation rate I'm using, I always see this multi-phase structure for the outflow. We can take a brief tour through the simulation. This is actually now just a rendering of the density field at a particular time. And I like this because it's pretty, and also it shows some of the, I think, salient features of this outflow that we sort of generically get. As I said, I've run a few of these simulations, but I'm only going to talk about this one today. So one of the things you can see regions in the disk where these clusters have actually cleared out the gas around them. You can also see, based on these sort of density contours, there are these higher density clouds that are being ejected, particularly near the center of the disk and at kind of low heights. But as you move up to higher heights and further out, you tend to get this more diffuse type cloud structure. And so all of the gas that you can essentially see in this rendering that's not see-through is gas that would be high enough density that it tends to be cool in these simulations. And so that gives you kind of a general picture of what these outflows look like. We can look, of course, in more detail at the simulation. There's massive amounts of data in these simulations. Basically, I store as much as I can. A single snapshot is something like 0.5 terabyte of data. And so we just store as many snapshots as we can, and we're pushing through the analysis as fast as I can do it. But some of the things that we've looked into, for example, is what does the phase diagram of this gas look like? So for here, I'm showing density on the x-axis, temperature on the y-axis, and this is just a mass-weighted histogram. So each of these bins, this is just showing you how much mass there is at that density and temperature. And for this diagram, I've actually x-sized the disk, so I'm just focused on the properties in the outflow. And what we can see is, this is a multi-phase outflow. It covers this large range in phase space, but it primarily is concentrated in these hot and sort of cool phases. And in this particular case, there's more gas in the cool phases, but we can measure those ratios, see if they change as a function of star formation rate or time in the burst and that sort of thing. So this is the kind of observation that we're then looking to compare in detail with those down the barrel observations, for example, to see if you measure a certain amount of mass flowing out in one phase, what does that imply for, say, the total mass outflow rate in an observation? Similarly, we can look in detail at the properties of the outflow as a function of radius and see how it changes. This is really interesting to me because I'm trying to come up with actually analytic models that we can write down that describe the properties of the outflow as a function of radius given, say, the star formation rate. And For example, in the density, right, if this is, now I'm showing the median density of the gas in the outflow, a 25th and 75th percentile to give you some idea of the range, and also the mean. And this is for the volume filling hot phase of gas, so it's relatively low density and it's falling off. We can also, then show, say, the gas that's cool. And this is showing you that clear separation between phases. And this is the kind of thing that, as we're developing these analytic models, we want to come up with models that can incorporate this multi-phase structure of the outflow, which is not something that people have done in the past. I can do this for any number of different variables, but this is a short talk, so I'm not gonna walk through all of these, but I do want to highlight the velocity. So if I go through and look just at this velocity slice, the hot gas is moving at of order 1,000 kilometers a second. That's what we expect for these outflows. But the cool gas shows this interesting trend that as a function of radius, it's increasing in velocity as we move out. And the reason that this is interesting is because this is effectively the properties of the cool gas that we see in those down the barrel observations. So this is related to that puzzle I was talking about of how do you actually get cool gas moving at high speeds in outflows? And this is something that I was interested in from the time that I was a PhD student, so I looked into it in more detail in these simulations. And to show you, for example, how this actually works, I'm going to now show some movies that just are slices of the simulation. So this is the density on the left, the temperature in the center, and on the right is something that I'm calling color. Color is basically just a dye that we inject into the gas, and I can give it any arbitrary value. For these simulations, I basically say any gas that was already in the simulation at the start has a color of 0, so you actually can't see the disk because the disk and the halo gas have the same color. And then gas that I inject into the clusters, the star clusters, I'm going to give a color of 1. And that just allows me to tell at later times in the simulation, in any given cell, how much of the gas in that cell was injected and how much of the gas was already present. And so if I start these movies, you'll see because it's a slice and the clusters are rotating that they come in and out of the view. So you'll see there one is kind of coming around and they go back. And what you can see in this color slice is that there's a tremendous amount of mixing happening in the outflow. And in fact, that, it turns out, is probably the dominant feature in setting the phase structure of this particular simulation. You can see there's clear correlations between the density and temperature, right? So as gas cools, it tends to achieve higher density. You can see there's times, as I said, when you get a lot of cool gas. I want to point out though, right, like this isn't necessarily associated with a specific color. It's all been well mixed. One of the reasons that's interesting is because if you, for example, were just accelerating gas from the disk via ram pressure, so taking discrete clouds and pushing them out, you would expect to see blobs of 0 color gas up here. And that's not what we see at all. And so this is actually a really interesting way to discriminate between different models that could produce this cool gas in the outflow. I'll just briefly mention, essentially we have, in this case, the sort of clear signature of acceleration due to mixing that we can measure because of this color variable. So I've plotted a histogram now showing the color of the gas against the radial velocity, and this is for the cool gas, but this relationship holds for all of the gas in the simulation. And this line just shows you what you would expect. There would be a linear relationship between color and velocity if all of the momentum in the cool gas was transferred via mixing with the hot gas, right? And what you can see is that the gas in the simulation follows this linear relationship really quite well. It's easy to get gas down below this line because if you're, say, decelerating it due to gravity, that would push you down here. And so this is really nice because now we have a really clear explanation for how you can accelerate gas in these outflows and a demonstration that you can get cool gas at large radius, which matches the observations. Another interesting feature of these simulations is that it naturally ejects metals from galaxies. And a way to see that is, again, by appealing to this color variable. So you can think of the color as a proxy for metallicity, right? And the way that works is you expect the most metal-rich gas to be the gas that is being injected in these clusters, because it literally represents the ejecta from supernovae. And so if we assume then that the metal-rich gas has the highest color, and we look at how that correlates, say, with the radial velocity, you see that the most metal-rich, least mixed gas is also traveling the fastest. So this is a really efficient way to distribute metals, outside of your galaxy and into the broader halo. So, a few conclusions from this particular small-scale study, right, is that if we add mass into these hot winds, into the hot phase by mixing with gas from the ISM, then they can cool down to 10 to the 4 Kelvin based on sort of reasonable assumptions about star formation rates, et cetera. And that's interesting because that is a theory that people have posited for cool gas in outflows, but not one that until this had actually been demonstrated. And that cool gas can be high velocity, so we can match the observations in detail using this model. We need clustered supernova feedback to do this, so I didn't have time to get into the details of this, but I'm happy to talk more about it offline. This only works if you have clusters, and so actually there's evidence that maybe the way that feedback and outflows work at high redshift or in high star formation surface density systems is qualitatively different than the way it works at low redshift, say in Milky Ways, partly because of the way that stars are forming and how clustered they are. And also, this mixing is really the key in this whole process. And so we need high resolution to capture that mixing. And that's the way that we actually are able to demonstrate this. So in the last minute or so, I just want to bring this back. I spent a lot of time talking about this sort of detailed small-scale study of one particular phenomenon, which was this numerical experiment. But what does this tell us about the broader context of galaxy formation? And so the idea, the method that I'm trying to employ is basically to use this as a multi-scale framework to inform our larger and smaller scale simulations. And so, essentially that super bubble simulation I was showing you demonstrates how you can connect simulations at these different scales. And we can do the same thing with these outflow simulations. We can connect them to larger scales. So for example, this is a simulation of a galaxy halo. This is just a slice through a quadrant by a collaborator of mine, Drummond Fielding. And the idea there is, now we can simulate halo scales, perhaps with slightly less resolution because we don't care as much when it's slightly lower pressure. But how do you know how to, say, inject mass and energy at the center of this simulation? Well, you can use the results of these, different scaled simulations in order to come up with these how you should connect these different scales. And reaching further back to the cosmological simulations, the idea is that we'd like to use these high resolution simulations to develop better and particularly more physically motivated and less arbitrary models for the feedback in those simulations, right? And so that, I think that's something that many groups are thinking about doing, and I think it's something that is really worth pursuing because it's the phenomenological nature of the feedback models right now that is keeping us from being able to make these predictive statements about galaxy evolution. And so if we can actually connect it back to the physics at small scales, then we can, I think, make a lot of progress. And people have done this successfully, for example, for unresolved turbulence in the ISM of galaxies. This is a well-tested method to do this sort of thing. And so I'll finish just by showing you another fly-through of a different simulation that I didn't have time to talk about. I should mention these visualizations in particular were produced with this NVIDIA software package, so I can't take all of the credit for producing these movies. But they're pretty, and I like to distract people before I take questions. So enjoy. And with that, I will take your questions.
Okay, thanks. Questions for Evan?
Thanks for the excellent talk, great pictures and movies. So I have two questions. First is, how different the implemented feedback prescription you use from like TNG simulation or fire simulation? And the second question is, how robust the result of your analysis is in terms of like if you change the feedback prescription, how it would change the velocity of the cool gas at CGN and in the outflows.
Right. Yeah. Yeah. So great question. So the kind of prescription I'm using isn't really very related to what's done in, say, something like Illustrious, where essentially they just have a star formation rate. Based on the star formation rate, they sort of throw gas out of the galaxy at a velocity that's determined by essentially what velocity do we need in order to match the stellar mass function. There are, plausible physical models that relate the properties of outflows to, say, the circular velocity of the galaxy, but it's still a phenomenological model. Fire's a little bit different, but I would say the main difference between what I'm doing and what, say, a Zoom like Fire is doing is that they can't resolve the actual feedback, say, the hot phase of the supernova feedback in their simulations, right? And it's basically just a density argument. Even in, say, a 10 parsec cube, that hot gas is very low density. So, a couple of solar masses, right? And their resolution elements are 10 to the 4 solar masses or something like that. So it's the difference is that we have the resolution to actually capture all of the physics, even though we are using still, a subgrid prescription for how that feedback is actually working. And in terms of how robust that model is, one of the reasons I ran a bunch of different simulations is to test that robustness. And it turns out that as long as the feedback is clustered, that the results of these analyses are pretty robust. You always get a hot phase that's moving at high velocity. You always get a cool phase that has this accelerating profile. You can change the amounts of gas in different phases based on the star formation rate. But it does depend on the clustered nature of the feedback. So if you just implement, all of your gas is in sort of a nuclear injection region, and you don't have this asymmetry, you don't have these clusters moving with the disk, you can get outflows that look qualitatively different. So it does, it has something to do with the way that you distribute the feedback. But the cluster model themselves, it doesn't matter, for example, very much if I include lower mass clusters, because they just don't have very much of an effect on the overall outflow properties. Yeah.
I heard a talk recently by Mark Vogelsberger about refining or improving their subgrid model for star formation, and showed, to my surprise, because I hadn't appreciated it before, that the illustrious TNG model had no cold gas in its phase diagram for the interstellar medium. And when they changed the algorithm to allow for that, they got a completely different structure for the interstellar gas. It went from smooth, beautiful spiral arms to lumpy, bumpy stuff. And that's the improvement.
Right.
In your case, I noticed when you chopped out the disk, there was no cold gas. So I have to ask, where did the cold gas go? And you don't see any spiral arms at all. So now I'm wondering, not exactly who to believe, but what to believe.
Right. There are a couple of things that I glossed over that I should clarify before I answer your question in detail. The first is that I have a temperature floor of 10 to the 4 Kelvin in my simulations. So it's not because I chopped out the disk that you don't see any cold gas in this phase diagram. It's because the coldest gas in my simulation is 10 to the 4 Kelvin.
So are we back to illustrious TNG
right.
before it now discovered the importance of putting cold gas in?
So the other difference is that I am not trying to simulate a multi-phase ISM. I am doing a calibrated numerical experiment, the goal of which is to measure the properties of the multi-phase gas between 10 to the 4 Kelvin and 10 to the 7 Kelvin in outflows, right? And so I designed an experiment that I thought could do exactly that. And so I would not claim that I am, trying to correctly reproduce the multi-phase ISM in the galaxy. The reason that my disks have this smooth structure is because I set them up that way, and I'm not trying to produce spiral arms either, right? I am trying to sort of distribute, in some cases, star clusters in what I think is a realistic way to demonstrate how they would interact with the gas in the disk. But I'm trying to do something that is fundamentally different than what a simulation like Illustrious or Illustrious TNG is trying to do. So there's no real conflict of, who should I believe in this case, because we're really doing very different experiments. Does that make sense?
Let me ask it in a different way.
Right.
In view of my having seen the experiment of getting the phase diagram with cold gas in one case and no cold gas in the other, what would the difference be in your results if there were cold gas?
Right. So, for the disk would look very different. For the outflow, obviously it has to be a conjecture because I didn't run this simulation with cold gas, but based on, say, those super bubble simulations where I did include cold gas, what I tend to find is that the coldest gas, that 100 Kelvin, the cold neutral medium, that tends to be destroyed. It doesn't get very far. So it gets, mixed in, basically, with the warmer phases of gas. So let's see if I can get this to play. Probably have to get rid of this.
I would also imagine, while you're doing that, I would also imagine that the metals that you talked about being in the ejector
Sure.
would be exactly where the coldest gas was, because the highest cooling rates would be there.
Well, it's not. It depends on the mixing, right? Yeah. And so I have not done this.
Maybe we can say that.
Yeah. So that's fine. Right. But
Maybe time for one other question before we wrap up?
sure.
Yeah. Sure.
I'm struck by many of your simulations showing very filamentary structure, including things like almost seems like a radial spice, or kind of seems like radial spice. And I wonder what that is coming from. That is to say, and that is seen in temperature, density. I am assuming that some of it is coming from thermal instability. I'm not sure whether that is the case. And these highly spiky structures, some instability, because the shock by itself, moving at the speed of 200 kilometers, will have a temperature of several million degrees, and will tend to wipe out many of the pre-existing structures. So could you say what's going on, and whether it's believable or an artifact or something?
Sure. So I think that sort of filamentary radial structure is very real, and I can get into a lot of detail, but right now, we're short on time and I'm over, so I'm not going to go into a lot of detail, but it essentially comes from the fact that the regions that are susceptible to cooling down to 10 to the 4 Kelvin are regions where you've mixed gas, where you've mixed 10 to the 6 Kelvin gas with 10 to the 4 Kelvin gas. And that's basically these envelopes of clouds. So you push a cloud out from the disk, you mix some of the gas on the edges, that creates this intermediate temperature, 10 to the 5, 10 to the 5.5 Kelvin gas, that's the most susceptible to cooling because it's at the peak of the cooling curve and it cools back down. And actually that wake focusing effect might be real. There's a number of small scale studies that are showing that might be real as well. And so you sort of expect to see that propagating out. And the fact that it tends to be very radial in the simulation I was showing was because I was putting everything at the very center, so then you expect this sort of radial structure. But yeah, we can talk more about it in detail after if you want to.
Right on. All right, well, let's thank Evan again.